Hello guys, welcome back to my channel, and today I have another grand integral for you guys that I'm going to be using a new method of integration on, namely the Laplace transform. So for all those of you who don't know what the Laplace transform is, you'll see that you'll learn about that today. So let's get to it. So we have the integral I being defined as integral from 0 to infinity of sine squared x divided by x squared times 1 plus x squared dx. Now see, the numerator, although it's a sine squared term, it's not a simple sine, shouldn't be much of a concern um, in the initial part, because look at the denominator. It's actually a product of x squared and 1 plus x squared, right? So it seems it calls for partial fraction decomposition. So what we're going to do finally is forget the sine squared x for now, because partial fraction decomposition is not a part of calculating this integral. It's a part of splitting the denominator. So we'll first split the denominator and then we'll multiply everything by sine squared x and then we'll integrate. Okay, so we have 1 divided by x squared times 1 plus x squared. So I want to split this into some constant divided by the first factor plus another constant divided by the second factor. But before doing that, I'm going to let p equal x squared. And this is not a substitution that is actually a part of integration. This is not a part of integration. So not an integration substitution. This is not a u, let's call it a u sub. This is not a form of u substitution that we need to differentiate both sides to get dp is equal to 2x dx. There is no dx in at least this partial fraction part. This is just substitution for algebraic convenience. So that enables us to write this in the form 1 divided by p times 1 plus p. And we can split this as follows: a over p plus b over 1 plus p, where a and b are constants. And for those of you who are familiar with partial fraction decomposition, this substitution might make sense to you guys, because say if we just split it up into x squared and 1 plus x squared, we would need a polynomial of degree less than the denominator, right? So if the denominator had a degree of 2 because of the x squared, we would need a degree 1. We would need a linear term. A would just not suffice. We would need ax plus b and bx plus c here, for example. So taking p equals x squared, we can completely avoid having linear terms, and we can do the process way easily. Fine, let's cross multiply now. We have 1 divided by p times 1 plus p being equal to a times 1 plus p plus b times p divided by p times 1 plus p. The denominators are cancelling out. This gives us 1 is equal to, we can group all the p terms. So we have, when we factorize out p, a plus b plus an a. P can be treated as a variable. Since there are no terms with p, the coefficient of p should be 0. So a plus b should be 0, and the only constant we have, a, should equal 1, right? For the equality to get satisfied. So a equals 1. And by this we have b equals negative a, and a is 1. So b is -1. Nice. We can therefore write this fraction as a. What's a? 1 over p minus 1 over 1 plus p. But what was p? X squared, right? So we can further resubstitute back. We get 1 over x squared minus 1 over 1 plus x squared. So using partial fraction decomposition, we basically split our fraction into, our fraction was 1 over x squared times 1 plus x squared. This is now equal to 1 over x squared minus 1 over 1 plus x squared. So, but what was remaining? What did we take out from the integrand? We took out just the denominator. So why don't we multiply both sides by the numerator, sine squared x? So we have sine squared x over x squared minus sine squared x divided by 1 plus x squared, and then we integrate both sides with respect from 0 to infinity with respect to x, 0 to infinity dx minus integral from 0 to infinity of this thing dx. So I is basically, this is I, right? This is I is basically the difference of these two integrals. So first is the integral from 0 to infinity of sine squared x divided by x squared dx minus integral from 0 to infinity of sine squared x divided by 1 plus x squared dx. And it looks like these two integrals have to be done separately because they are problems in themselves. So we call this I1 and we call the second part along with the negative as I2. Therefore we have the grand equation I is equal to I1 plus I2 because we are also taking the negative, therefore we have a plus I2 here. So let's do I1 now. See you on the next page. So as discussed, I1 is basically integral from 0 to infinity of sine squared x divided by x squared dx. And what's the interesting fact about sine squared x? It can be split into using the double angle formula for the cosine. So we can write sine squared x as half of 1 minus cosine of 2x. The denominator is x squared as it is. Well, it seems that we can again split this. So I1 becomes half of the integral from 0 to infinity of dx over x squared minus half of integral from 0 to infinity of cosine of 2x divided by x squared dx. So now taking the negative outside to compensate for the antiderivative of 1 over x squared, we get negative half 1 over x evaluated from 0 to infinity minus, again we can use integration by parts here. I made like a bunch of videos on calculating integrals of this form. So again taking the minus out for compensation with the antiderivative of the denominator, we have cosine of 2x as it is divided by x minus integral from 0 to infinity. The derivative of cosine of 2x is negative 2 times sine of 2x. So negative negative positive 2 times the sine of 2x divided by x and a dx. So we have I1 now equaling, well, when we plug in infinity, as x tends to infinity, this will go to 0, minus limit as x tends to 0. So minus minus will make a plus, half times the limit as x tends to 0 of 1 over x. This is essentially an infinity. This blows up to infinity, but let's just keep it in this form because in the hopes that this might cancel off with something else. We have to evaluate this from 0 to infinity, don't forget that. So as x approaches infinity, the cosine of 2x will just keep oscillating between -1 and 1, it is bounded. We don't need to worry about that blowing off to anywhere. All we need to worry about is the denominator. So as x tends to infinity, 1 over x will go to 0. This thing entirely will go to 0. Minus, because we're subtracting upper limit minus lower limit, half of, well, cosine of 2 times 0, cosine of 0 is 1. So we just have limit as x tends to 0 of 1 over x, because cosine of 0 just became 1. So we have 1 in the numerator. And x is again, as x tends to 0, 1 over x will blow up to infinity, but we just keep it in this form, and you'll see in a minute why. And when we open the bracket, this half and this 2 will cancel out, giving us just the integral from 0 to infinity of sine of 2x divided by x dx. So I1 is now, well, these terms, look at the limit, forget half, but look at these limits, they are the same, right? So they are cancelling out nicely. It's a great thing because we got rid of our infinities finally. So we just have integral from 0 to infinity of sine of 2x divided by x dx, and this is just equal to pi over 2. And why is that? Because remember, I told you I made a bunch of videos on these type of integrals. So we found out that if we have integral from 0 to infinity of sine of ax, where a is any constant, divided by x dx, this is always equal to pi over 2. See, the constant is 4, 5, 6, 7, any integer, anything, this will always be pi over 2. So that's why we obtain a pi over 2 here. Check out that video if you want the derivation, why this equals pi over 2. So we basically know that I1 equals pi over 2. Now, as we discussed, I2 is going to be negative integral from 0 to infinity of sine squared x divided by 1 plus x squared dx. Now again, we can split the sine squared x using the double angle formula for the cosine. We get negative integral from 0 to infinity of 1 minus cosine of 2x, and we have a half, so negative half 1 plus x squared as it is dx. We can take the negative in and switch the order of the numerator. So we have half of integral from 0 to infinity of cosine of 2x minus 1 divided by 1 plus x squared dx. Now we can obtain two integrals from this. We have half of integral from 0 to infinity of cosine of 2x divided by 1 plus x squared dx minus half of integral from 0 to infinity of dx over 1 plus x squared. So for our purposes, let's call this j, and we'll do this on a fresh page now, because this is quite complex, unlike what we had for I1. So let's just write j, and we'll do it at the end of this. So with j minus half of, well, this is easy, right? Integrating this is easy. We have inverse tangent of x from 0 to infinity. So I2 is just j minus half of, well, tan inverse of infinity is pi over 2, tan inverse of 0 is 0. So we have j minus half of pi over 2 is pi over 4. So j minus pi over 4. So let's do j on the next page. See you there. So again, as discussed, we have j being equal to half of the integral from 0 to infinity of cosine of 2x divided by 1 plus x squared dx. Now, for all you avid viewers, you might remember that I had done my first video of complex analysis on a similar integrand, on a similar integral. So in that video we had cosine of x divided by 1 plus x squared. Again I think from 0 to infinity, or I think negative infinity to infinity. Here we have cosine of 2x. We can do this with complex analysis, but as the title of this page suggests, and also the name of my YouTube channel, name of my YouTube video, I'm going to be using something that's called the Laplace Transform. So what is the Laplace transform? What is a transform? First let's start with that. What is a transform? So remember that, say we have a function, what, say, defined from real numbers to real numbers. What does a function do? It takes in a quantity on R1 in this case. You plug that in and it outputs another quantity, let's call it y, that's on R again. So it takes in one variable, gives out another variable. But what a transform does is it takes in a function. It does not take in a single quantity like x or y. Say you have a transform a, it takes in a function and spits out another function. It's sort of a function of functions. It's like a super function. So that's essentially what a transform is. So now let's talk about the Laplace transform. So we have, say, the Laplace transform of a function. Remember, it takes in a function, and it always takes in a function of t, being defined as integral from 0 to infinity of e raised to negative st times f of t, that function, integrated with respect to t, and that outputs another function which is not a function of t but a function of s. And so this is used a lot in physics and engineering, because say t is like the time domain. You put in the time domain, you get out a function of, say, another domain like the frequency domain. So basically that's how a Laplace transform is defined. There's this fancy L and these fancy brackets of a function of t, always a function of t, being defined as the integral from 0 to infinity of e raised to negative st times f of t dt, and you get out, that spits out another function which is a function of s. So how are we going to use the Laplace transform, as as we planned in to calculate our integral j? So remember first that we need to have a function of t. So how are we going to do that? We can just parameterize, right? We can have j of t, like we can parameterize like we do for Leibniz rule or Feynman integration. So we have half of integral from 0 to infinity of cosine of 2tx divided by 1 plus x squared dx. This is how we can parameterize our original j, such that our original j is nothing but j of t when t equals 1. If you plucked 1 over here, you just have cosine of 2x over 1 plus x squared dx, which is exactly j. So after all our processes of simplification and stuff, we just have to plug t equals 1 to get back to our original j. Right now we are sort of generalizing for t, that's why we parameterize stuff, and also for the requirements of this Laplace transform. We needed a function of t, we made it a function of t. So let's take the Laplace transform of both the sides. So we have Laplace transform of j of t is equal to, well, half is a constant and Laplace transform is an integral, so you can take the half outside the integral. Half of, using the definition of the Laplace transform, integral from 0 to infinity of e raised to negative st times, what's the function? This part, right? This inside integrand. This integral actually, not just the integrand, this integral entirely. So integral from 0 to infinity of cosine of 2tx divided by 1 plus x squared dx, and then don't forget the dt of this dt. So it's sort of a double integral that we have here. So now you guessed it, assuming in uniform convergence of both of these integrals, of basically both of these functions on this range of 0 to infinity, we can interchange them. We have to obviously prove using Fubini, Tonelli and stuff like that, but let's just leave that for this video. Let's assume uniform convergence, let's just interchange both of them. So we have the Laplace transform of j of t being equal to half of integral from 0 to infinity of, well, when we are interchanging dt and dx, we will also get interchanged, right? So dx is to the outside, so let's just write this integral inside. We have e raised to negative st times cosine of 2tx dt first, and then whatever x terms are there, we can just pull them out of this inner integral because they do not depend on t. The only thing we have like that is 1 over 1 plus x squared, and we have an external dx. So this dt integral is placed inside the dx integral, right? I hope you see what I did there. It's basically like interchanging sums and integrals. So whatever terms only depended on x, did not depend on t, can be taken outside the t integral, right? Because they are a constant when we are only concerned about t. But these terms, e raised to negative st and cosine of 2tx, depend on t. So they have to be placed inside the inner integral, while the external integral is over x, and then you can pull the terms that only depend on x outside the inner integral. So I really hope you see what I did there. So this is going to be half of integral from 0 to infinity of 1 over 1 plus x squared, and notice what this thing is. We can use our definition of the Laplace transform to recognize that this is nothing but the Laplace transform of cosine of 2tx, and we have a dx term. Nice. So what we do now is, we have a formula sheet. There is a standard formula sheet available of Laplace transform, especially if you are studying at the university level. They provide you with this standard formula sheet. So you can look at that to notice that the Laplace transform of cosine of a constant a times t is going to be s over s squared plus a squared. And remember that I had said that the Laplace transform spits out a function of s, so we should not be surprised when we get s outside over here as a result of the Laplace transform. But so in our case, we have the Laplace transform of cosine of 2tx. So what's a? In our case, a is nothing but 2x, right? So we can just directly use this formula and plug in a value for the Laplace transform of cosine of 2tx. And I'm actually going to make a new video on this, proving this, a video where it will be only focused on finding the Laplace transform of this new by hand manually. So stay tuned for that. So now in our case, we have the Laplace transform of the j of t being equal to half of the integral from 0 to infinity of, we can just plug this in, so s as it is, s divided by s squared plus, what's a, 2x, right? A squared will be 4x squared times this, don't forget this 1 over x squared that was waiting all this time, and dx. So now notice that s is a constant with respect to x, so it can come out of this integral to get s over 2 times the integral from 0 to infinity of dx over s squared plus 4x squared times 1 plus x squared. Well, looking at the denominator again, it seems that we've complicated everything, but don't worry, don't panic, because looking at the denominator again, we can again perform partial fraction decomposition, PFD, like we did for splitting up our denominator initially in our original unmanipulated problem. So let's perform partial fraction decomposition. I'll just clear all the mess, all the calculations that we did on this page. So as a consequence of our calculations, we end up with this crazy expression for the Laplace transform of the j of t. So now, as I said, we have to perform partial fraction decomposition. So we've, forget the integral for now. We have 1 over s squared plus 4x squared times 1 plus x squared. Now again, as we did in the start of the video, let say a constant y equals x squared, and this is not an integration substitution. This is not a substitution done in the process of integration. This is an algebraic substitution. That's why I told you to forget the integration. This is basically like the first part of this video, the initial part of this video. So we have 1 over s squared plus 4y times 1 plus y, which can be split as c over s squared plus 4y plus d over 1 plus y. Again, cross multiplying everything, we have 1 over s squared plus 4y times 1 plus y being equal to c times 1 plus y plus d times s squared plus 4y divided by s squared plus 4y times 1 plus y. Denominators will cancel out. We have 1 is equal to, let's collect all the y terms. So we have y times c plus 4d and c plus ds squared, which will act as the constant term. So now notice that there are no y terms on the left hand side, so this coefficient of y, c plus 4d, has to equal 0, and this being the only constant term has to equal 1. So c plus ds squared equals 1, and c is nothing but negative 4d, so we can substitute that over here. So negative 4d plus ds squared equals 1, and when I collect the d's, I have d times s squared minus 4 being equal to 1. Now divide everything by this term. We have 1 divided by s squared minus 4. What's c? Is negative 4 times d. So negative 4 times 1 over s squared minus 4. So great, now we can actually make a substitution. So we have c divided by s squared plus 4y. So negative 4 over s squared minus 4 divided by s squared plus 4y plus d over the other part 1 over s squared minus 4 divided by y plus 1, and now that's equal to, well, we can reverse substitute. Y is nothing but x squared, right? Now bring the constant down. We have 1 over s squared minus 4 times 1 over s squared plus 4x squared. Sorry, this will be 1 over y plus 1 because I'm writing the positive term first, minus 4 over s squared minus 4 times 1 over s squared plus 4 times y. Now let's, in the place of y, let's substitute x squared plus 1 and s squared plus 4x squared. So this is going to equal nothing but our original integrand, which is x squared plus 1 times s squared plus 4x squared. Now let's integrate both sides, 0 to infinity dx. Doing that on both sides, dx, integral from 0 to infinity dx. And don't forget that we also had this extra factor of s by 2 over here, as s by 2. So again, multiplying and dividing s by 2, we get, well, we multiply s by 2 over here, we just end up with the Laplace transform of j of t, and we have to multiply s by 2 here. So s by 2 times, this can be taken out because there's no x, s by 2 times 1 over s squared minus 4 times the integral from 0 to infinity of dx over x squared plus 1 minus s by 2 times 4 over s squared minus 4 times the integral from 0 to infinity of dx over s squared plus 4x squared. Well, this can be done easily. This is just the inverse tangent. So s by 2 times 1 over s squared minus 4. So inverse tangent evaluated from infinity to 0. If you want, let's just, I'll just do this. Inverse tangent from 0 to infinity minus, you can cancel out a 2 here. So negative 2s divided by s squared minus 4. Why don't we get rid of the 4 associated with this x squared? So factorize the 4 out. We have integral from 0 to infinity of dx over, we took out a 4, there was no 4 here, so we have to divide by 4. 4 is 2 squared, so s over 2, the whole thing squared, right? This will be s squared by 4. That will satisfy the equality, plus x squared because we took out the 4 here. And now we end up with s by 2 times 1 over s squared minus 4. Tan inverse of infinity is pi over 2, tan inverse of 0 is 0. So we just have pi over 2 minus, well, we have, I would actually like to keep this 2 around, or let's just cut it out. So we have s over 2 times 1 over s squared minus 4 Well, we can use the formula for these type of questions. X squared plus constant squared is basically 1 over this constant. So 1 over s by 2 is 2 by s times the inverse tangent of x divided by this constant. So x divided by s over 2 will be 2x over s evaluated from 0 to infinity, because it was a definite integral from the start. So pi over 2 times this 2 will have pi over 4 times s over s squared minus 4. Well, this term is entirely going to cancel out. Negative tan inverse of infinity is pi over 2, tan inverse of 0 is 0. So we just have pi over 2 times 1 over s squared minus 4 over here. So the Laplace transform of j of t is equal to pi over 4 times s over s squared minus 4 minus, I would like to have a 2 in the numerator, and you will see in a minute why. So 2 in the numerator, 2 in the denominator, we'll have pi over 4 times 2 over s squared minus 4. And I also want to write 4 as 2 squared. You'll see in a minute why. So we have this expression, this relatively condensed expression for the Laplace transform of j of t. Now we just want to obtain an expression for j of t. So what do? How do we get rid of the Laplace transform? Well, in case you're thinking about the Laplace transform as a function, we're going along the right lines, because there exists something called the inverse Laplace transform. So it basically reverses what the Laplace transform does. It takes you from the capital F of s that the Laplace transform spit out to a small f of t that the Laplace transform took in as an input, and it's written as, like a Laplace inverse of f of s, for example. So and when we apply inverse, say for example, if you think about the transform as a function, a super function, say we have f inverse of f of x, the inverse and the function itself will sort of cancel out, giving us just the argument x, right? So the same thing, if we apply inverse Laplace transform, that will cancel out with this Laplace transform, giving us an expression for j of t. So I'm going to do exactly that on the fresh page. See you there. So we had an expression for the Laplace transform of j of t as follows: pi over 4 times s over s squared minus, now 4 I wrote as 2 squared, you will see why, minus pi over 4 times 2 over s squared minus 2 squared. So I suggest taking an inverse Laplace transform of the Laplace transform of j of t. So that will give pi over 4 is a constant. Again, it can be taken outside the inverse Laplace transform. Inverse Laplace transform of s over s squared minus 2 squared. And the Laplace transform, inverse Laplace transform, is also distributive over subtraction. So minus pi over 4 times the inverse Laplace transform of 2 over s squared minus 2 squared. So what the inverse Laplace transform is actually asking us is, what function do you input in the Laplace transform so that you end up with this as your Laplace transform. So this expression, for example, s over s squared minus 2 squared is a Laplace transform is a Laplace transform of which function of t. So if you have your as I said, your table of Laplace transforms, you might notice this and trace it back to some function. So, and in case most of us don't have that sheet right now, so I'll just write the Laplace transform, the inverse Laplace transform. Say we have the Laplace transform of a function cosh of 80, the hyperbolic cosine of 80, that is just s over s squared minus a squared, and we have, say, the Laplace transform of sinh of 80, the hyperbolic sine of 80, that is just a over s squared minus a squared. And when we let a equal 2, that's where you get s over s squared minus 2 squared, which is exactly this. So if we take inverse on both sides, we end up with just a hyperbolic cosine of 80 being equal to the inverse Laplace transform of s over s squared minus a squared. So this term is essentially this. Same thing goes for this. When we plug in a equals 2, you have 2 over s squared minus 2 squared, which is exactly that. So inverse Laplace of this is just the sinh of 2t, and over here we have cosh of 2t. And like I suggested before, the inverse Laplace transform of the Laplace transform of j of t is just j of t itself, which can be written as pi over 4 is outside, times inverse Laplace transform of s over s squared minus 2 squared, as discussed, is cosh of, well, a can be taken as 2, right, following this formula, 2 times t minus pi over 4 times, and as discussed before, this is just the sinh of 2t. And since, as I told you, the Laplace transform takes in a function of t, gives out a function of s, the inverse Laplace transform does the opposite, takes in a function of f and gives out a function of t. So don't be surprised when you see a t over here. It's actually a sign of doing your inverse Laplace transforms correctly. So now I want to take the pi over 4 in common. We have the cosh of 2t minus the sinh of 2t. That's going to be, we can use the definitions for these quantities. Cosh of 2t is e raised to 2t plus e raised to negative 2t divided by 2, and the sinh of 2t is, well, we have a negative, sorry, e raised to 2t minus e raised to negative 2t divided by 2. And the minus is sort of acting on this term entirely, so it's best to bracket that like that. So j of t finally becomes, we can factorize out the 2's, so we have pi over 8 times e raised to 2t plus e raised to negative 2t minus e raised to 2t minus minus plus e raised to negative 2t. These terms are proudly going to cancel out. We just have pi over 8 times e raised to negative 2t twice, so 2 times e raised to negative 2t, and notice that j of t is going to be the, well, 2 and 8 we can reduce. We have pi over 4 times e raised to negative 2t. So now we have a very nice and compact form for j of t. But remember what I had said, what did we actually want to find? We wanted to find j, right? And how is j related to j of t? So j is nothing but j of t when t equals 1. So let's make that substitution here. Pi over 4 times when t is 1 e raised to negative 2, that will be pi over 4 e squared in the denominator. So we know our j, we can plug this in our expression for I2, because j popped up during I2. So let's go back to that. So we know j now. So I2 is nothing but pi over 4 e squared minus this pi over 4. Fine, we know our I1, we know our I2 finally. Let's go back and plug it in our grand equation. Our grand equations suggested I is equal to I1 plus I2. So I is going to be, I1 we calculated as pi over 2, and we know I2 as pi over 4 e squared minus pi over 4. This will further reduce down. So pi over 2 minus pi over 4 is pi over 4 plus this term pi over 4 e squared. So again the pi's pop up out of nowhere, and although this was a really long one, this was an extensive approach, and I just introduced the Laplace transform to you guys. So using Laplace transforms for doing integration is also one of those rare methods of doing integration by non-elementary techniques. So complex analysis, Feynman integration, Laplace transform, you can use them to do integration. I mean, you can do one integration in one definite integral in many different ways. I mean, we could have done the part that I said, to use Laplace transform on, basically the cosine of 2x divided by 1 over x squared, cosine of 2x divided by 1 plus x squared from 0 to infinity dx. We could also do that using complex analysis. I can probably make a video on this, but it's not going to be any different. It's just we would have different residues because of the cosine of 2x, and we would essentially end up with the same result that we got. So in conclusion, what did we learn today? We learned that I, which was defined as integral from 0 to infinity of sine squared x divided by x squared times 1 plus x squared dx, is just pi over 4 plus pi over 4 e squared, excuse me, which roughly approximates to 0.891692. So it's small number, less than 1, but I mean it's a really beautiful result. We have pi's and we have e's. We used a Laplace transform. We first split this using partial fraction decomposition. We got two integrals. We calculated one, basically using integration by parts and using a standard result that we knew from past videos. And then the second integral I2 also got split into two parts. We called one J. We did the Laplace transform of that. Did the inverse Laplace transform of that. We got compact form of J of t. Substituted t equals 1 for J. We found out J, plugged it in our I2. Then we finally, for the grand finale, we had I1, we had I2. We plugged in those values in our grand equation of I equals I1 plus I2. We got pi over 4 plus pi over 4 e squared. So I hope you really enjoyed this video and learned much. Please don't forget to like, share and subscribe to my channel. Recommend me if you like. I'll be doing these trick integrals and on these relatively difficult questions side by side along with my high school calculus series, because although I don't know, it's probably I'm doing this at a wrong time. I mean, during exam time it was really a hit with people, because I've noticed I've got less views for my high school calculus series. So it seems I'll be doing it less frequently compared to these kind of videos, but let's see. I want to complete that too. I just don't want to leave any playlist incomplete. So that's it for this video, guys. Stay home, stay safe. Have a great day. Peace out.